a little red round button on the display. Good. Okay. I return. Anybody who wants to see cute baby photos after class may come down to and I have a few on my phone. So, a lot to talk about, not a lot of time to talk about it in. I don't think there are any announcements particularly. You guys got the assignment 3 grades yet? No? No. Okay. I'll do some butt kicking on that front before the end of the week. Before the end of the week. Everything must be done before the end of the week. So, might as well just keep motoring on then. So we were talking about bitwise arithmetic. I'm going to need one of these. So bitwise arithmetic, of course, something that you will come to know and love by the time you've finished your degree program, as many of the embedded systems domain applications require the direct manipulation of bit information at the register level. Put short, your labs next semester are going to require bitwise operations, so you should learn them now and spare yourself the indignity later. So, we had talked about bitwise and bitwise OR operations. Just in general, if you take two numbers, right, encoded in, ooh, this is a nice job. It's like higher quality than usual. Right? If you take two binary numbers, a bitwise operation goes one at a time examining the bits and performing some operation just on those bits. One thing that distinguishes bitwise operations from things like addition and subtraction, there's no possibility of carry bits being produced. So that is to say values which are transferred from one place value to the next, or vice versa. As a consequence of this, all of these bits can be processed in parallel rather than being processed sequentially. An addition circuit must process things sequentially. Therefore, bitwise operations are often mapped to individual logic gates, right? So, basically, if you have the, terminal 1, terminal 2, run them through an AND gate, and then that's your output terminal. Have one of these for each bit in the two numbers, and that is what bitwise AND operations are in terms of physical circuitry. Make sense? Good. So, you guys are doing a course on digital logic at the moment? So this should be familiar territory for you guys, right? Not everything is NAND gates. Even though you can use NAND gates for everything, not everything is NAND gates. So, pardon me. So we have and we have or. These are both reasonably easily, distinguished. XOR might be one that you haven't heard of before. Have you guys done XOR gates? Okay, so you'll know a bit about this then. Very simple. If the two inputs are the same, then the output is 0. If the two inputs are dissimilar, then the output is 1. Right? So now we come to left and right shift operations. Also reasonably simple to understand. Pardon me. So, like you ever have like a gas bubble that's like just underneath your larynx, so it makes it difficult to like project your voice? That's what I've got right now. So left shift operation, right? Not very difficult to understand. None of these operations are difficult to understand if you think about them in terms of binary data, right? A left shift operation shifts all of the numbers X number of places to the left, right? So in this particular case, this is a big endian system. That is to say, we are considering values on the left side to be of greater place value than values on the right side. When we shift values over by X number, in this case, this is 1 being illustrated, however many bits on the left side, a number of bits equal to the number you're shifting by on the left side will be lost. They will be deleted, they will cease to exist, they will be no more. They will be pushing up the daisies, all right? On the right side, we backfill with zeros. So any space that does not have a number traveling from the original number into it gets a 0 put in. Make sense? Effectively, the left shift operation, at least in big endian systems, constitutes multiplication by 2 to the power of y, where y is the number of bits you're shifting, right? Because, that's just what it is, right? Multiplication itself is actually a very complicated circuit. So if you are just multiplying by some power of 2, it's actually a hell of a lot faster in terms of, circuit time at least, to perform a left shift operation rather than a full multiplication, right? And this doesn't necessarily come up in C programming, because when you're programming in C, everything's being clocked by CPU clock cycles anyway, so it takes as much time to perform one addition as one shift operation. They because they're clocked by the CPU, and the CPU goes at a fixed rate. But you will see it in energy savings, right? The less circuit that you have to use to process something, the less energy that circuit requires, which means that you can, reduce the amount of excess heat generated by the CPU, which, actually does have practical applications in servers, right? I may have talked about this with you guys before. What's the number one cost that goes into keeping a server farm?
Temperature regulation?
Air conditioning, yeah. Yeah, absolutely. Because the computers heat up, you have to dissipate the heat or else they'll melt, right? So if you're using smaller, more efficient circuits to do your processing, you're wasting less energy, which means you don't have to pay as much for the air conditioning, right? Very small amount, but if you go through a program that is run very frequently and you optimize it according to this type of stuff, and if you have a sufficiently large server farm, enough CPUs running this thing, it can actually have an impact. Remember economies of scale, right? Even if you, as an employee, save like 0.0005 cents per production unit, right? If your company makes 10 billion of them, you've still paid your salary, right? So, anyway, so that's left shift. Right shift is symmetrical. You just move the whole thing n bits to the right instead of to the left. Again, backfilling with zeros, this time on the left side, and anything on the right which is outside of the frame of the things that are getting shifted gets destroyed. Yes? Any questions? in the same way that the left shift is multiplication by 2 to the power of n, where n is the number of bits you're shifting by, the right shift is division by the same. Because, of course, we're just shifting things over by place value. You know, if you took the number 130 and shifted all the place values down by 1, you'd end up with 13, which is the same thing as division by 10. Right? Make sense? Okay. Good. 1's complement is the easiest one. You literally just take each bit and apply a NOT gate. Enough said? Hopefully? Good. So, just to prove that you can do a lot of things with these things, these are subtraction and addition using bitwise operation. I'm not going to go through them in detail because I'd like to keep moving here. Instead, I'd like to skip the entirety of the next section and do a demonstration on the board to show you what 2's complement is if I haven't already in this class. Did we do 2's complement? No? Maybe? All right. Well, we'll do 2's complement then. So, so some of you may have noticed sometimes if you are applying the wrong print, the wrong type of print tag to a negative number, it may look like it's very, very large, right? This is due to the manner in which negative integers are encoded inside of essentially all computer systems. So, rather than do the stuff that's in the slides, which is long, boring, and confusing, and I've since learned a much better way to teach this, I'm just going to do the better way of teaching it. Projector. There we go. So, negative numbers. Our goal for the development of a system of negative numbers is that we should be able to work with both negative and positive numbers with as little fuss as possible. In theory, we would like to use the same circuitry for adding both positive and negative numbers, right? So let's consider how we might go about encoding negative numbers, right? It should be obvious that we need some way of telling whether or not the number is negative or not. Inside of the number, this would be one bit dedicated to the sign of the number, right? So we might have, a number composed of 4 bits, whether it's positive or negative, should be indicated by one of those bits, right? Also known as the sign bit. The naive approach is to simply separate the sign bit out, call it the sign bit, and the rest of the number is just the rest of the number, right? So we then have, 0, 1, 1. In general, 1 means negative, 0 means positive. It's like one of those arbitrary decisions that people made in the past, like, whether the charge of an electron should be negative or positive, that type of thing. So, if we have a 1 here, that will yield negative 3. Right? This is known as sign magnitude notation, because the magnitude of the number is denoted by a particular set of bits, and the sign is separate and upfront. Sign magnitude. Make sense? So let's explore some reasons that this is bad. All right? So let's consider the number 7, right? Positive 7. So if 1, 0, 1, 1 is negative 3, then 0, 1, 1, 1 will be 7, right? Now remember, what we wanted to do is we wanted to have it such that we could add negative numbers to positive numbers and have the result just work, right? So let's attempt binary addition over these two numbers, right? So 1, 0, 1, 1, 0, 1, 1, 1, and we're going to add these and we're going to see what we get. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 0, 1, 1, 0, 1. Of course, this falls outside of the bounds of the integer that we're currently working with, so we destroy it. Later on, we can use it for other things. We can, use that kind of thing, but for now, we'll just throw it off. So we can see that, according to sign magnitude notation, 7 minus 3 is equal to 2.
Yes.
Right. Which, of course, is not the case in ordinary arithmetic. So this is not, we're not yet there. Right? Question?
Why did you carry the 1?
For the same reason that you carry it in decimal arithmetic. Right? So in decimal arithmetic, if you had like 5 plus 4 plus, like 55 plus 45, right? 5 plus 5 is 0, carry 1. But the reason that you carry the 1 is because this number would be 10, and 10 is the amount that the base system is, so you have to pop that 1 to the next one, right? It's the same thing in binary. So if I've got 1 and 1, right? That would be 1, 0 in binary, right? But this means I'm overflowing this bit's size, so this has to be added to the next column. So it's like carry rules in regular addition. It's just the base system is 2's instead of 10's. Make sense? Any other questions? Cool. All right. So, in addition to the fact that this means math doesn't work, we are presented with one additional problem with this type of notation. All right? We have two zeros. So both 1, 0, 0, 0 and 0, 0, 0, 0 yield negative and positive 0. And if this doesn't make your skin crawl, then I don't know what to tell you. So imagine, if you will, just for a moment, you're trying to implement some kind of a circuit, right? And your circuit, every time a 0 might appear, has to check to see if it's a positive or a negative 0, right? Like, the only people who get away with this type of nonsense is people doing calculus who are like approaching 0 from the positive or the negative direction. And even then, 0 itself is neither positive nor negative. It's indicating a direction of approach, right? So positive and negative 0 is a terrible idea. 0 should just be 0, right? So this is another reason why sign magnitude is bad. Make sense? So you might be saying, all right, so give me the straight dope. What do we do about this problem? To borrow some nomenclature from the 90s. So we'll perform the same arithmetic. We'll still do 7 minus 3, but let's try something else. Let's try one's complement, right? So, or just the complement. So, in normal arithmetic, right, or in normal binary representation, 7 is 0, 1, 1, 1. 3 is 0, 0, 1, 1, right? So we want negative 3 we want to take all of these bits and flip them. This will be our first approach, right? So let's try representing negative 3 as just regular 3 with all of the bits flipped. You will note the final column, this column right here still indicates sign. So long as you don't allow numbers higher than 7 in the 4-bit example, right? 8 would be, to include 8 would be to destroy the number system, right? But so long as values are less than 7, this bit on the leftmost side still indicates sign, which is good, right? We still have some easy way of telling whether a number is positive or negative, right? So let's perform this arithmetic. So, in this case, 7 minus 3 is equal to 3. And we have a carry bit. Now, it turns out that in one's complement arithmetic, you have an interesting property where if a carry bit is generated here, if you wrap that around to the beginning and add it, then you get the correct answer. So, if we perform the end around carry, then we end up with 7 minus 3 equaling 4. Ta-da! We're still not quite there yet, though, right? We still have the problem of 2 representations of 0, right? Using one's complement, all 4 being 0, that's still 0. And all of these being 1, that's also still 0. Right? Again, this is not something that is desired. Any questions so far? Yes?
I don't understand how you carried it over. Like, what were you doing with the carry one? You brought it around?
So, my results that I ended up with was 0, 1, 0, 0, 1, 1. But this had a carry to the next place value, right? So, basically what I said is, in my algorithm, right, if this is 1, then I have to perform one more step, which is 0, 0, 1, 1 plus 0, 0, 0, 1, which is this carry bit, right? If this is a 0, then you can put a 0 in here and it has the same effect. But if you do that, that's 1, carry, 1, carry, what am I talking about? Sorry. That's 0, carry 1, 0, carry 1, 1, 0, which is equal to 4, which is equal to the correct answer. Make sense? Good. So, we move now to the actual representation which is actually used in modern computing systems. 2's complement. Two's complement is, there's a simple mnemonic device to remember what 2's complement means. 2's complement is actually it's 1's complement plus 1. So they just sort of took the 1 and put it with the other 1 and made 2. So this tells you, this gives you the formula for how 2's complement is actually calculated. Right? So going back to our example again, 7 remains the same. 3 is 0, 0, 1, 1. Negative 3 now becomes the 1's complement of the positive value, and you add 1 to it. Make sense? So let's see how this works. Zero, 1, sorry about the chalk. So you'll notice that's the correct answer. Right? So what 2's complement is basically doing is it's pre-establishing the end around carry. Right? So that's not the cool part though. I'll show you the cool part. The thing that 2's complement finally solves is the problem of having 2 zeros. Right? So let's say we have 0, right? Let's see what happens if we apply the negative transformation to obtain negative 0. Right? So the first thing we do, flip all the bits. There we go. The next thing we do is add 1. So that'll be 0, 0, 0, 0, 1. Throw that off, and boom, you're right back where you started. So there is only one representation of 0 under 2's complement arithmetic, and it is the one that you would expect. Does that make sense? Cool. Yeah, so that's how negative integers are actually represented, is using 2's complement arithmetic. So the reason that your numbers sometimes look like they're very, very large, if they're negative and you're printing them wrong, is because your come on. Oh my god. Oh no. Oh no. Okay.
Unplugging it.
Plugging it, what?
I think the technology goes unplug it, replug it back in there once. I don't know if there's a plug though.
Yeah, try turning it off and on again.
The building.
Yeah. I don't think I have access. Oh, and I can't even get at the thing because the unlock controls are through that as well.
That's funny.
Oh. Nah, we can manage.
Exactly.
Yeah, because actually the rest of this is kind of math on the board kind of stuff anyway. So we've had a slight failure of the technological system, which I'm not going to make a joke about this being symptomatic of the greater, the more large decline of Western society as a whole. Not this time anyway. This time it's just technical problems. So what we're going to do, for those of you listening from home, from now on I will call out the slide that we're on. Pretty much everybody in the room has some way of viewing slides. I will try to minimize the degree to which slides are necessary, but that's how we shall see out the remaining 16 minutes of this class. So there you go. So I get the opportunity of showing everyone in the class that I don't actually need the slides, that they are an assistant and not, it's not the slides that are the prof, and the prof is just speaking for the slides. The prof is actually, capable of doing a lecture. So, for those of you who are making reference to the slides, through my demonstration of 2's complement, I intend to not cover the 2's complement material as presented in the slides, because I think I have found a better way of explaining it and I didn't have time to update the slides. So, we're going to talk about graph theory. Just a little bit, just a taster. All right? So, as computer people, we write algorithms to solve problems, right? The algorithms that we can apply to solve problems are more or less effective based on the computational models which we use, the mathematical models, right? An array is a mathematical model, right? Since we are now C programmers, we know that inside of the computer itself, the array is just a sequence of data which can be accessed via index, right? The concept of an array itself is a mental model, a mathematical model for what computers do. I am about to introduce to you another very important one known as the graph. All right? So this is not graphs as in plotting graphs, scatter plots, and that sort of thing. This is a collection of nodes and edges. So a graph might look something like this. You have a series of vertexes. 1, 2, 3, 4, 5, 6. All right. So you have a set of vertexes, each of them being labeled, and you have a set of edges between these vertexes. So as not to imply a connection. So, how many people have played Ticket to Ride, the board game? Yeah, that's basically that board game is based in graph theory. So, graphs are extremely, you can model a large number of things in them. You can model ports or computers inside of a computer network, right? You can model physical ports on the planet's surface and various routes of connection between them. You can the number of things you can model with graphs is extremely large, right? Anytime you have a field of things and you want to see whether things are connected or not, a graph is a good way to go about it. So, graphs are a very general form of mathematical model, right? Particularly this type of graph, which is what we might call an undirected graph, right? I'm now looking at, before I get there, sorry, I was on slide 25, I'm now on slide 26. So the way that we might encode a graph like this, there are more fancy ways of doing it if you take an algorithms class like you're going to take next semester, but from a mathematical perspective, an edge is designated by the two vertices it connects. So in this case, our set of edges is 1, 2, 1, 3, 1, 6, etc., etc. Make sense? Question?
Do we do that for each one of them, right? So
Yes,
it's
yeah,
not
yeah.
just these.
Yeah, so 2, 3 is 1 as well. 3, 4 is 1 as well, etc., etc.
And we don't repeat this, like,
Yeah.
don't do too long.
So in this form of graph, you don't, because these are, like, there's no direction implied, right? However, so we get to different scenarios that we use this model for by applying new properties to this very general form, right? One property we apply is arrowheads. So by taking these edges and deciding that they travel in a particular direction, right, we go from an undirected graph to a directed graph. So we might say, you know, there, up, down, sideways, etc. Right? I'm gonna flip this one just for the purposes of examples. So, if the edges are directed, the way you represent them is from the source to the destination, right? So in that case, it is possible to have two edges connecting the same two vertices. It's just they will be traveling in different directions. So in this case, 2, 1 is in there, but also, or 1, 2 is in there, but also 2, 1 is in there. Make sense? Good. So directedness is an important property, right? We have another important property, cyclic or acyclic. All right? So if it's possible, on picking a particular vertex in the graph, to return to that vertex via the nodes, or via the edges of that graph, pardon me, then it is a cyclic graph. Is this a cyclic graph? Yes or no? Thumbs up for yes, thumbs down for no. It is. That's a cycle. Right? So, depending on whether a graph is cyclic or acyclic, right, you have different types of data structures which arise from it. Have you guys heard of trees? Trees are directed acyclic graphs. Not trees like outside. Jesus Christ. Okay. Ha ha. Oh, incidentally, do you know what a set of disjoint trees is called? No, branches are the things inside the trees. Do you know what a set of so a tree, right? This is what a tree looks like in computing. All right? This is a binary tree. Generally, there's implied direction here. But binary tree, right? We've got a directed graph, acyclic, no cycles are permitted to exist, and each parent has at most 2 children. So technically you can have like one going off here and then 2 more over here. Still a binary tree. Okay? So, do you know what a collection of these things is called that are unconnected to each other in mathematics? It's called a forest, yeah. Yeah, there we go. Anyway. So why am I telling you all of this? And how could this possibly matter in the last, 4 minutes of class? So, if you take the graph, right, in C, take vertexes and make structures out of make vertexes out of structures in C, right? So that each of these nodes is a structure, right? What do the edges become? This is a C programming class, so the word should never be far from your lips. Pointers. So it is possible, nay, very useful, to model a graph in C programming as a series of structures which point to other structures. So, to take, for example, the binary tree. Let's say, just for the sake of interest, that we've got some numbers inside of these. All right? Etc., etc. You would have a structure, struct node, int value, struct node pointer left, struct node pointer right. So, what these things end up actually looking like in code. If you imagine structures as being boxes containing some things, right? This would be 10, so value, left, and right. You would make another one that would have a value of 3. It would have left, and it would have right, right? Or I didn't put them right. This left will point here, right will point somewhere else. Am I making sense? A little bit, hopefully. So, that's how you do a binary tree in C. Right? The nodes of the tree can be and should be dynamically allocated. You can have insertion procedures for these trees so that you follow the tree down, find the right place in the tree for the thing you're trying to insert, malloc yourself a new node, take the address of that new node and put it into the correct pointer slot inside of the tree's structure. Right? Question?
And then would you make like an array or what to store all the different nodes? How would you do that?
You don't need one. You need one pointer to the root node in the data structure. All other elements of the data structure are accessible by recursively following pointers. Does that make sense? So we're now talking about we're talking about math where recursion is your natural solution for a lot of these types of problems, right? Not to say iterative solutions don't exist, but you'll see anyway. So now we come to I hope you guys are paying attention because this is the type of stuff they put on interviews, very, very seriously. So let's imagine, just for the sake of argument, that we wanted to start off more simply than this. All right? Let's take a graph where each node points to at most one other node. So it's like a binary tree, except for each parent having at most 2 children. Each parent has at most 1 child, and no node is pointed to more than once. What you end up with is a data structure which is linear and resembles an array to an extent. But you have to keep in mind that these things are still structures containing a value and a pointer, except for the last one, which points to like a null or something like that. Yes?
Could you make the last one point to the first one?
If you make the last one point to the first one, then you have a circular linked list, which is a specific type of data structure. It's a useful type of doubly linked, well, we're getting ahead of ourselves. Yes, they exist, and yes, they are useful, but this is just a very simple one called a singly linked list. So, we will explore linked lists and all of the beautiful, wonderful coding that can result from them next time in class. Thank you very much.